Hi, great, thanks. Yeah, I'm Ethan. I am an assistant professor at the University of Wisconsin-Madison. This is work that I did with my old PhD advisor at Cornell and a couple of his current graduate students. So before we actually get started, SCIF stands for something. It is the Smart Contract Information Flow Language. So this is going to be a bit of a change of pace from what we've been hearing for the last couple of hours. This is going to be a much more sort of computer science-y, more technical direction talk. Right, so we often think of security in a lot of contexts as putting up a wall around some sort of application. Right, so in smart contract land, if we have a smart contract, we might put up a security wall so that an attacker who tries to get in is just going to automatically get sent away. But in smart contract systems, this isn't really what things look like, right? We don't have a single contract that we can put up a wall around. We have like a lot of different contracts in the system, and all of these contracts are interacting in sometimes complicated ways. And in fact, some of these contracts are actually going to be malicious, but we don't really know which ones. And to make matters worse, an application here isn't one contract. It's actually a bunch of different contracts that are connected to each other in sometimes complicated ways. And this is where SCIF comes in. So SCIF is a new programming language for smart contracts that tries to make trust assumptions within the system and between those contracts very explicit. We've modeled it after Solidity so that it's hopefully at least somewhat familiar looking and feeling to developers. And it has a lot of built-in security features that allows us to stop entire classes of attacks. And the idea is that there's sort of particularly pernicious types of vulnerabilities, and we want to be able to eliminate those vulnerabilities entirely. And we do this inside a completely open system. And open systems are very complicated, but that's what we have to work with. And so we have, there are a lot of attackers. The attackers might be running code that we have no control over. They might be running code that's not written in this programming language and does things that are literally impossible to do in this programming language because they're insecure. And we need to know that we're going to work, things are going to work, they're not going to break anyway. And so I want to talk about two of the big classes, the really difficult classes of vulnerabilities that SCIF is designed to handle. And that's reentrancy and confused deputy attacks. And for those that aren't familiar with this, I want to go through how these attacks work and how they relate to trust and how we can get that into the programming language to actually head them off at the pass. Okay. So to see how reentrancy works, I want to take an example of a simple automated bank. This is, assume this is a smart contract running on a blockchain for now. And the bank has one large pile of money, and it keeps track of a balance sheet that says maybe Alice has $50 in her account and Bob has $10 in his. And if Bob wants to come in and he wants to send some money, $10 to, say, Widget Corp, the bank is going to follow a very specific transfer protocol. The first thing it's going to do is it's going to check Bob's balance. He asked to send $10. He has $10 in his account. All is well. Great. The next thing the bank does is it sends the money where Bob asked him to, and it asks, and it alerts the recipient. So in a system like Ethereum, it's going to do this just through a standard function call. At this point, the recipient, so Widget Corp, it can update its logs, it can mark that Bob sent the money, whatever it is, pocket the $10, and return control back to the automated bank. So now that the bank knows the transfer was successful, it can go ahead and decrease Bob's balance down to 0 and return completing the transaction. But let's say Bob's not a normal user, right? He's not trying to politely send $10 to Widget Corp. He's trying to steal money from the bank. And Bob has an idea. This time, he asks the bank to transfer money directly back to him. So what does the bank do? It follows its steps. It sends Bob there we go. It checks Bob's balance, got $10, no problem, sends him his $10, and alerts the recipient. But the recipient in this case is Bob, and Bob controls his own alert function. And Bob here is malicious. So unlike the honest recipient, Widget Corp, we saw before, Bob doesn't just update his logs and return. Instead, Bob sends the bank another message. He says, hey, bank, please send me $10. Right, so he re-enters the bank while the bank is waiting for a return from its alert. what does the bank do? It's an automated system. It follows its transfer steps. First, it checks Bob's balance. Because the first transfer hasn't completed yet, the bank hasn't decreased Bob's balance on its balance sheet. It still thinks that Bob has $10 in his account, so this check passes, and it moves on, and it sends Bob his $10 and calls Bob's alert method again. Bob can keep doing this over and over and over and over and over again, and he can extract way, way, way more money than is actually in his account. I don't know, maybe $50 million more? That's not just a random number. So some of you may recognize this example. This isn't an arbitrary automated bank I came up with. This is a slightly simplified version of the distributed autonomous organization, the decentralized autonomous organization, or the DAO, the original DAO from back in 2016. This was an Ethereum contract that lost about 3.5 million Ether to this exact attack. At the time, that was worth about $50 million, hence the number on the slide. As of a couple days ago, that would have been worth about $11 billion. I haven't checked in the last 2 days. But this resulted in Ethereum taking the really extreme step of hard forking to undo the damage. This caused the split. If you're familiar with the difference between Ethereum and Ethereum Classic, this is what caused them to fork off. And it actually caused a lot of people back then to fundamentally question the idea of smart contracts in the first place. And it took a lot of time to sort of get momentum on this as both a research and practical area going again afterward. So there's been work trying to eliminate reentrancy, right? I wasn't the first one to see this and go, hey, something's wrong, we need to fix it. But all of the previous work on this really focuses on single contracts. And in doing so, they assume that applications are one smart contract, and so they secure one contract. They put a wall around a single contract rather than securing an entire application. And this results in a definition of reentrancy that we call object reentrancy. And unfortunately, object reentrancy is inherently non-compositional. And so what I mean by that is if we have a single monolithic application, and that application calls out into something else, and the something else calls back into the first application, this is considered reentrant. This is a reentrant call. But if we refactor that monolithic application into a functionally equivalent modular application, so we just have two different pieces, when you plug them together, they do exactly the same thing. If we analyze those modules separately, we get a totally different definition and a different meaning of security. Because a call from one of the modules into a second application that then calls back into a different module is not considered reentrant, despite the fact that this is actually functionally equivalent to the monolithic thing on the left. It has exactly the same behavior. And so combining modules into a larger application gives us a different definition of reentrancy and a different definition of security. And this lack of composition makes it really hard to secure large systems and large applications that are made of a bunch of different pieces. And it can miss complex multi-contract interactions, which have opened up attacks in the past. Some of you may be familiar with the reentrancy attack that hit Uniswap in 2020. That involved a complicated multi-contract interaction. So our approach in SCIF is to identify that reentrancy is fundamentally about trust. Right? So if we look at the DAO, what happened here is that the DAO implicitly trusted Bob to pocket his money and return after it sent him $10. And Bob violated this implicit trust when he made his reentrant call instead of just returning. And SCIF makes this trust explicit in the code itself, which means that it's able to identify this bug before you even deploy a contract. While you're writing the code, it can identify the bug, it can help the programmer out, and it can tell them, hey, this is dangerous, and help them figure out how to fix it. The other kind of vulnerability I wanted to talk about is something called confused deputy attacks. And so confused deputy attacks have been around for decades in a lot of systems and have been extremely damaging in smart contracts in particular. So as an example, let's look at a simple DeFi exchange here. And if Bob wants to exchange a token, he calls that exchange, and the exchange has two steps. We're going to go through sort of the same structure we had before. First thing it does is it swaps the relevant tokens. So it's just going to call out to some token contracts. And then it's going to execute a callback that Bob gave it to alert anyone who needs to know that the swap has happened. In this case, maybe it just tells Bob, hey, the transfer worked. But again, let's see what happens when Bob tries to attack the system. This time, Bob's idea here is to send a malicious callback that instructs the token, with a callback is to instruct a token to send the exchange's money to Bob. So how does that work? Well, the exchange executes its instructions. It runs the swap, and then it runs the callback that Bob gave it. And the callback here is to call the token and ask it to transfer the exchange's money to Bob. And since that call is coming from the exchange, the token will say, yes, everything's good. And the token will go ahead and send the exchange's money to Bob, which is really not what's supposed to happen here. So in this case, the exchange is acting as a confused deputy. It's acting on Bob's behalf in a way that it should not because it has been confused. This attack is actually another violation of implicit trust. The exchange here trusted that the callback would be something that was safe to call on Bob's authority, something that Bob probably could have called anyway. And Bob violated that implicit trust when he sent the token transfer instruction in as the callback. And again, SCIF is going to make this trust explicit within the code, as we'll see in a minute, and it checks automatically to make sure this sort of confusion isn't happening. So to see how to use these insights, that things are fundamentally about trust, we need a way of tracking trust. And we do that using a powerful existing tool that's designed for this purpose, something from programming languages literature called Information Flow Control, or IFC. To use IFC, we need to label data in computation to track how different inputs affect outputs. IFC is most commonly applied to confidentiality to prevent data leaks, but here we're using it for integrity. So in our example, maybe we have, say, trusted and untrusted, and we allow trusted data to influence untrusted data, but not vice versa. So to apply IFC to the DAO, we need to label the code and the data. We're working from the DAO's perspective here, so we'll start by labeling the money and balances as trusted. And the transfer steps are code that actually needs to directly influence those balances, so we're going to mark that as trusted as well. It's part of the application. This is fine. But Bob might be trying to attack the system, so we're going to mark Bob as untrusted. Using these labels, we can distill down the complicated idea of reentrant executions into something really, really simple. And to do that, we're going to look at the pattern of trust on the call stack while this attack is happening. So Bob is untrusted. Bob calls the DAO, which is trusted, and this transfer method is then going to call Bob again, who's untrusted. To this point, everything's fine. Nothing has gone wrong. But when Bob makes a reentrant call, we get another trusted operation on the call stack. And this pattern of two trusted operations that's separated by an untrusted one, that is how we define reentrancy. And to enforce security, we need a way to make sure that reentrancy doesn't actually cause problems. We do that by locking integrity in the system. And so when an execution enters trusted code from untrusted code, it gets new integrity. We lock that new integrity, right? So if we have trusted and untrusted like we had before, when Bob calls withdraw for the first time, we're going to lock the trusted integrity level. And then the rule is that we're going to prohibit regranting integrity that's already locked, but will allow other calls to occur if they're not getting new integrity that's already locked. So the send call, this transfer operation that the bank made, that was lowering integrity. So that's fine. We still let that through, no problem. But when Bob tries to make a reentrant call, when Bob tries to make a reentrant call, the lock is going to prevent him from regranting trusted integrity, so everything works fine here. We can use the same idea with confused deputy attacks. So again, we're going to label Bob as untrusted, same reason he might be trying to attack the system. And here we're going to, in this example, the exchange and the token are coordinating. They have to collaborate to get things done. So we're going to label them both as trusted. But we need to be really careful, because that callback that Bob gave us, that came from an untrusted source. And so we need to label that as untrusted as well. And in fact, SCIF is going to force us to do that. It's going to force us to label that as untrusted because it came from an untrusted source. But remember, the only reason the call went through in the first place was because it used the exchange's authority. So this lets us to define a confused deputy attack. I'm out of time, apparently. This lets us to define a confused deputy attack as a call that uses trust that it shouldn't even have access to in the first place. And we can fix this by verifying calls, right? So the way that we do this is we provide a little extra information. There's a little bit of cooperation between the caller and the callee. The caller includes what they think they're calling. So in this case, the exchange is going to say, well, I think I'm calling this untrusted callback Bob gave me. And then the callee just checks to make sure that actually matches what it is. In this case, the token says, I'm not an untrusted callback that Bob gave you, so no, this is not allowed. It errors out. And in this case, we're able to stop the attack. And in fact, we can stop the attack without eliminating any intended functionality at all. So to very quickly sum up, right, we've got these compositional integrity-based definitions of both confused deputies and reentrancy. We're able to enforce security in this system even when we are interacting with unknown code that might not play by the same rules. And there's a bunch more features that I didn't have time for, right? We have secure exception handling. We have a mechanism for dynamic trust management in the language. There's a prototype compiler that's going to be available soon, and as of literally like 2 hours ago, there's a preprint of the paper available on my website. So I apologize for running a little over time, but I would be happy to take questions.
Question, yeah. I love information flow. So there are a lot of companies and like verification companies in the Web3 space, and do you understand like what kind of bugs are they inspecting for? Like is this reentrancy the main type of bugs they are fixing for these blockchain companies? And also, like, let's say if the world would adopt SCIF, then do we still need these verification companies, or are they also actually doing something more than just?
Yeah, that's a really good question. So there are a variety of different categories of vulnerabilities for this. One thing that some of them are looking for, the verification companies are looking for, is they're looking for sort of programming patterns, or sometimes they are looking for things like reentrancy and confused deputy attacks. We don't think they're doing a very good job for those, but there are other types of vulnerabilities, things like numeric concerns, integer underflow and overflow, certain types of checking, of validity checks on inputs and things that SCIF doesn't really help with. It's not designed to help with. Those are still major concerns. We think some of those verification practices are doing a very good job there, and some of those companies are still absolutely necessary. There's also questions about functional correctness. At the language level, we're not trying to address functional correctness questions. That's very application specific. There are a lot of verification companies that are trying to analyze functional correctness, and we think that would hopefully play very nicely with the kinds of things that SCIF is trying to do, and that they would really, having both is better than only having one.
So another question is, like, if you were to redesign, let's say, the Ethereum's programming language, like, which of these defenses would you actually build into the language itself? I would imagine, like, something like reentrancy is like, we should just build it into the language itself.
Yeah,
right?
That's a really good question. So I would actually probably I would want to build in something like a confused deputy protection, because we think we know how to do that in a way that's not particularly restrictive. The reentrancy protection is actually a bit more complicated, and we don't. Our definition of security against reentrancy isn't no reentrancy. It's that reentrancy doesn't change the behavior. It doesn't allow the executions to do things that they couldn't have done anyway. We have a conservative approximation of that. We're sound, but there are all sorts of executions that don't do different things that we're disallowing. And I would be very hesitant to build something into the language itself that's that over-approximate, that's that imprecise. And so I'm not sure I would actually want to put the versions of reentrancy protection we have now into the protocols themselves. I think with some more research, we might be able to find better, more precise ones that would be worth putting in, though.
But also, like, suppose we are going to deploy something like this, is this annotation, will it become, like, will it be something that normal programmers can use, or is it simple annotation? Or
we hope the answer is yes, because we're structuring the annotations to be based around addresses, so both contracts and wallets as sort of the core principle, like bottom lowest layer of trust this or don't trust this. And then we've got a bunch of defaults in places that we think are very sensible and we think are making things much easier to use. But one of the directions for future work that we're interested in this is we want to actually run studies on this. We want to get people to use this language and figure out what does and doesn't work for actual programmers.
I see. So like, also, if let's say the lazy programmer doesn't annotate anything, and then like they still rely on these verification companies, and maybe they'll make it simple because now they just have to annotate the program for the, and then the compiler will automatically detect a bunch of bugs.
It will detect some things as per before, right? It'll detect some things and not others. It'll stop certain types of mishandled exceptions. It'll stop reentrancy. It'll stop confused deputies. It won't stop numeric overflow and underflow. Right, so you need both halves. Yeah.
Okay, thank you very much.
Great, thanks.